Okay, so now we have a very straightforward, I think, section 15.3 is graph theory for weighted graphs. There are 3 sections on weighted graphs. This is the first one on what's called the minimum spanning tree. In order to develop what we need for the minimum spanning tree, we just need a few definitions, and then we're going to see it's pretty straightforward. So first definition, a cycle is a walk that begins and ends at the same vertex. The book includes but has no other repeated vertices, and that's not really true, but has no other repeated vertices. Maybe that's the definition they want you to use. It's not accurate, but if it's their definition, it's their definition. Definition. So before we do the next definition, so what's a cycle? You start at some point, you do a bunch of edges, and then you get back to the same point that you began. So that is a cycle. A tree is a connected graph. It's got to be one piece, connected graph with no cycles. If you think of an actual tree, the branches don't kind of, as a general rule, come back and reconnect to the tree, right? Once you go along a branch and you reach an end, it's kind of like a dead end. So every way of going is a dead end. There's no ways of coming back. Definition. A spanning tree, which is the the opening title for the section, the minimum spanning tree. A spanning tree is for a graph. Is a subgraph, which is a tree and contains all the original vertices. So you are allowed to remove, remember what a subgraph is. A subgraph is you can take away vertices and edges left and right, and as long as every edge has 2 vertices at its endpoints, it's a valid subgraph. It's a smaller graph inside of the original graph. A spanning tree is a subgraph if it's a tree, no cycles, and all the original vertices are there, which means you can only remove edges. And finally, definition, a minimum spanning tree. A minimum spanning tree is a spanning tree of least weight. So when you add the weights, you might have more than one possible spanning tree, and each of the spanning trees will have a different weight. A minimum spanning tree is one of least weight. And the goal of this section is going to be to, given a graph, is to find its minimum spanning tree. And we're going to illustrate this with the following example. So here's A, B, C, D, E, F, G, H, back to A. Already we see we have a cycle, but that's not it. We also have that, and that, and that, and that, and that. And don't forget, this is a weighted scenario, so every one of these must be weighted. So the goal is to remove edges and end up with a spanning tree. Now that part's easy. The question is, how do I know it's a minimum spanning tree? So we have 2 algorithms that we're going to learn. The first one is called Kruskal's algorithm. And Kruskal's algorithm is as follows. Step 1, pick any edge of least weight. In our example, there are 3 of them. Pick anyone. I don't care. He doesn't care. Nobody cares. Pick an edge of least weight. Step 2, add any edge of least weight that does not form a cycle. Step 3, repeat step 2 until done. Until done. So let's do it. What we're going to do is we're going to start by just putting all the vertices, because we don't know which edges we're going to include, but I do know that I have to include all the vertices. Okay, step 1, pick any edge of least weight. So there's 3 of them. The book picks BH, so let's pick a different one. Let's pick DF. Okay, pick the edge of least weight. We got 3. Step 2, add any wedge of least weight that does not form a cycle. Well, we got 2 to choose from. Let's do DE. Whoops, DE. No cycle yet. Repeat step 2. Add an edge of least weight that does not form a cycle. Well, BH doesn't form a cycle. Next, no more 3s. We got 4s. This one, FE, I can't pick. That would form a cycle, but I can pick CD. That doesn't form a cycle. Another 4, I can pick BC. That doesn't form a cycle. Oh, I can do AH. That doesn't form a cycle. Now I just need G. So there's no 3s or 4s left that do not form cycles. 5 will form a cycle. 6 will not form a cycle. And I have my minimal spanning tree. What's the weight? 3 plus 3 plus 4 plus 4 plus 6 plus 3 plus 4. That is 27. What is the context of this problem? Find the minimum cost of connecting all the houses on an estate. Now they're all connected. The units are thousands of yen. So cost, min cost is, oops, they're not dollars, it's yen. Not yen, it's euros. The minimum cost is 27,000 euros. That's Kruskal's algorithm. Perfectly valid algorithm will get you the right answer every time. Here's another algorithm, Prim's algorithm. Now, if you go back to Kruskal's algorithm, oh, I want to do it in red. Oh, OCD time, red, Prim's algorithm. So if you look at Kruskal's algorithm, it's all about edges. Pick an edge, add an edge, add edges, edges, edges. You keep adding edges. Prim's algorithm, 1, pick any vertex, any vertex. Step 2, add an edge of least weight to the tree obtained so far that does not form a cycle. And step 3, repeat step 2 until done. Repeat step 2 until done. Okay, that's Prim's algorithm. So let's start with the, well, I don't gotta draw it, but let's start with that picture there. It says pick any vertex. Let's pick G, which was the last vertex obtained in the previous algorithm. And now it says add an edge of least weight to the tree obtained so far. Well, so far I just have G. So I have a 6, 7, 8, 9, so I have a 6. That's the least weight obtained so far, so we have a 6. Then I can add BH to the tree obtained so far. That's the least weight so far. I got a 4. I got 2 4s. So I'll do that one. Another 4. I'll do that one. Ooh, now I get a 3. I'll do that one. Another 3. I'll do that one. And I have one more 4. I'll do that one. And look at that. We actually end up with the same spanning tree, which means the minimal cost is still 27,000 yen. That's what's going to be the minimal cost. You can't have two different algorithms that are valid algorithms give you two different answers. It doesn't work that way. Now, be aware that even though in this case both spanning trees were the same, it doesn't have to be. The actual spanning trees that you end up with might not be the same, but their weights will be the same. Both algorithms will always provide a minimum weight and minimum spanning tree. And now what we're going to do is another example where we use Prim's algorithm, but this time we're not actually going to draw the graph. We're just going to look at the weight table. So I have no loops because a loop will not be a tree. 40, 45, 25, 10, 40, 25, 15, 30, 45, 25, 20, 35, 25, 15, 20, 15, 10, 30, 35, 15. So here's how we do it. Step 1, pick any vertex. The book picks vertex A. Let's pick a different one. Let's pick vertex C. So C is going to be our first pick. So what we're going to do is we're going to cross out all the numbers in column C and pick the smallest weight or a smallest weight in row C, which is 20. So that means D was our second choice. We're going to erase the numbers or cross out the numbers in column D. And now we're going to find the smallest number in rows C or D, which we have two choices. There's two 15ths. Let's pick this one. Not that I couldn't pick the other one, makes no difference, but we're picking E number 3. Cross out all the numbers in column E, and then find the smallest number in row C, D, or E. I got a 10, that's A. That's my fourth choice. Cross out A. Pick the smallest number in A, C, D, or E. That's the other 15, which finally takes us to B, which I can cross out if I want. So what do we have here? A is connected to E with weight 10, and E is connected to D with weight 15, and D is connected to C with weight 20, and B and D are also connected with weight 15. So we have a minimal spanning tree of weight 60. Done. Notice, by the way, if you look in the original table, if we look at the original graph, just to have it off to the side, look us here, the original graph, here's A, here's C, here's D, here's, whoops, here's B, and here's E. The original graph, A connects to everything, to C, to D, to E, and to B. I'm not putting the weights in, just the graph itself. B connects to A, C, D, and E. So there's D, there's C, and there's E. Actually, it looks like everything connects to everything. So C connects to E, to D, and D connects to everything as well. So this is the original graph. And essentially what we've done is we removed the EC connection. We removed the EB connection. We removed the AB connection. We removed the AD connection. We removed the CB connection. And we removed the AC connection. So we just removed a bunch of edges to get a minimal spanning tree. So with that said, let's move on now to exercise 15F. There's 7 problems. Question number 1. It says use Prim's algorithm to find the minimum spanning tree for the following graphs beginning with vertex A. State clearly the order in which the edges are selected. Exam hint, it says, it is likely an exam question will require this as evidence you performed the algorithm correctly. In other words, just getting the final answer is not enough. Maybe you even used the wrong algorithm. So here's A. So we're using Prim's algorithm, which means we pick any vertex, but they told me specifically to pick vertex A first. I'm going to first make a picture of the original graph, just so we have it here. A, B, C, F. Connection there, connection there. E, D, C, okay. And we have 5, 9, 6, 8, 7, 10, 13, 8, and 9. Okay, so let's use Prim's algorithm. He says start with A. So A comes first. So if you recall Prim's algorithm, we pick any edge that connects to A of minimum weights. And the answer is, in this case, there's only one, F, which means A and then F. Now we look at A and F and pick the edge of minimum weight that connects to either of the two. And I have a 5. So that gives me E. And now we look at A, F, and E, and I pick the edge of minimum weights, and I have F to D is 6. And then I look for the minimum weight now, and I have a 7 from D to C. That's 7. C is next. And then I notice that the only point missing is B, and I can connect to B from A. So my order is A, F, E, D, C, B. That will be the order in which they were selected. B. Oh, wow, this one looks fun. I get a circle. We have A, B, C, D, E, F, and a G inside. A to G, B to G, C to G, D to G, F to G, but no E to G. And then we have some numbers, 11, 10, 15, 9, 14, 10, 13, 20, 18, and 17. Oh, missed this one, 12. So we are now going to use Prim's algorithm. And the book says, start with A. Okay, no problem. We got A. Coming out of A, we have a 10. We have an, oh, well, first, I keep saying this, but it should be obvious. Always pause. So A to B, that's 10. Okay, looking at B, we have a 15 and a 17, but A has an 11. So to F, oh, so B and then F. Okay, so I can even cross the 11 and the 10 out. Maybe it'll help me see what comes next. So let's see, F, we got a 13, which I think takes the cake. So F is now going to go to E with 13. And I have a 14 that comes out of E to D. So we got 14. Oh, I got a 9, which goes to C. Didn't have that before. So 14 and 9 are both done. Out of all the numbers left, I have a 10 from D to G. That's 10. And I have all my vertices. So that is the minimum spanning tree created by Prim's algorithm, starting with A. C. we have A, B with a weight of 6, C with a weight of 3, D with a weight of 5, E with a weight of 7, F with a weight of 6, and that one has a weight of 4, and that one has a weight of 5, and AC has a weight of 7, and EC has a weight of 8. And we're going to again use Prim's algorithm. Again, you should be pausing and doing it yourself. So we start with A. We have a 4, 6, or 7, so we're going to use the 4. So A, then F with 4. And then coming out of A or F, I see a 5. C. Coming out of C, I see a 3. I don't think anything beats that. To B. So that's out. And then coming out of A, B, C, and F, I see a 5. Down to D. And then I have a 6 coming to E. And that should be the minimal spanning tree performed by Prim's algorithm in that case. And then for part D, oh, wow. So here's A. Here's B with a weight of 8. B goes to C with a weight of 10, which goes to D with a weight of 6, which goes to E with a weight of 10, which goes to G with a weight of 12, which connects to A with a weight of 9. G and B connect with a weight of 7. There's an F in the middle. And B to F is 6. And E to F has 5. And C to F has 7. And G to F has 11. Looks like that's it. So we're now going to use Prim's algorithm. So we start with A. A has an 8 or a 9, so we're going to use the 8. A to B. B, A. B has a 6, which goes to F. Smallest number that I can see in the graph is a 5, which connects to E. Smallest number I see in the graph is 6, but I can't use it because I don't have C or D yet. Next number is a 7, which I can use. 7 connects F to C. Now I can connect to D versus that 6. Smallest number on the graph is another 7, which goes B to G. And it looks like I have A, B, C, D, E, F, G. I have all my points. I have my spanning tree. Thank you, Mr. Prim. I assume his name is Prim, otherwise why call it that? Okay, question 2. Use Kruskal's algorithm to find a minimum spanning tree for the graphs in question 1. Why am I not surprised? So let's duplicate this. Okay, so now we are going to Kruskal's algorithm it. And it does not say, it says list the order in which the edges are selected. Well, what does Kruskal's algorithm say? It says pick any edge of least weight. Unlike Prim's algorithm, where you can pick any vertex you want, in Kruskal's, you have to start with an edge of least weight. So an edge of least weight is 5. So we're going to start with EF. So EF is our first edge. Now we pick any edge we want anywhere of least weight that does not form a cycle. So I'm going to form FD, which is 6. Next, I can form DC, which is 7. So 5, 6, and 7 are done. I have a couple 8s here that I can use. One of them will form a cycle, so I'll have to do the other one, which is this one, FA. I can't use that 8. That forms a cycle. That forms a cycle. AB. And then this forms a cycle, and that forms a cycle. So I'm done. Minimal spanning tree, A, B, C, D, E, F. I have them all. How does that compare to prims, by the way? If we look at them, it's the same. Hopefully, they won't all be the same, and then we can compare the weights. But for now, they're the same. So let's duplicate that one. Okay, B. Now let me erase these crossouts. Okay, so B, we're gonna use Kruskal's algorithm. Edge of least weight, that's this one here. CD has a weight of 9. Next edge of least weight anywhere in the diagram, we have GD, a weight of 10. I have an 11. AF is 11. Not attached, don't care. Prim cares. Kruskal does not. A11. Next, I have a 12, but that forms a cycle. Next, I have a 13, F to E. Next, I have a 14, E to D. Next, I have a 15, B to C. 17 forms a cycle, 18 forms a cycle, and 20 forms a cycle. So how does this compare to what we had earlier? It's not exactly the same. So let's count the weights. For the one up here, 10 plus 11, 21, 34, 44, 58, 67, 14, 28, 38, 47, 62. Let's double check our work here. D, D, E, F, G. I do have them all. The one up there, let's use my calculator to make sure I don't make a mistake. 10 plus 11 plus 13 plus 14 plus 9 plus 10 is 67. 11 plus 13 plus 14 plus 10 plus 9 plus 15 is 72. Huh. Okay, well, let's check again what happens. I picked A, then I did 10, which was the cheapest or the smallest. Then I did 11, which was the next smallest. Then 13, which is the next smallest. Then 14, which is the next. Then 9, then 10, at which point I had them all. So here, CD was 9. Then I did GD, which is 10, AF, FE, ED, and then B. Oh, no wonder. Silly me. BC is not smaller than, I don't even miss that 10. That's crazy. Oh, how did I miss it? AB, and that gives us the same one. Oh, yeah. I am somewhat embarrassed. But as always, if it's wrong, don't give up, persevere, find your mistake. So now, Kruskal. Let's delete those. So starting with the edge of least weight, I have a 3. So I have BC with a weight of 3. Next one that's lowest is AF with a weight of 4. Next lowest is CD with a weight of 5. Next is FE. Let's move that F over a little bit. FE with a weight of 6. Next is, oh, actually, before that, FE should have been FC with a weight of 5. And then FE with a weight of 6. And then AB has 6, but it forms a cycle. 7 forms a cycle. 7 forms a cycle. 8 forms a cycle. So I have the same picture that I had before. And then finally, we have D. Again, we're going to use Kruskal. Let me remove these. Okay. Okay, pick an edge of least weight. I see a 5. F to E, 5. I see a bunch of 6s. I see F to B for 6. F to B. And I also have C to D is 6. So those are basically the same in terms of which one comes first. Then I have some 7s. I have C to F, but I also have BG, and those are again same order. And then I have 8, which is AB. I think that's the only 8. AG forms a cycle, so that doesn't count. ED forms a cycle, doesn't count. BC forms a cycle, doesn't count. GF forms a cycle, doesn't count. GE forms a cycle, doesn't count. So that should be the same one that I had before, and it is. So in this case, not only did Prim and Kruskal give 4 spanning trees that were the same weights, but they were actually the same spanning tree themselves. Question 3. Determine the number of edges there will be in a spanning tree containing V vertices. If there's 1 vertex, there are 0 edges. If there are 2 vertices, there can be 1 edge. If there's 3 vertices, there can be 2 edges. If there's 4 vertices, there's most likely going to be 3 edges. It looks like the pattern is that for the number of vertices, it's 1 fewer than that is the number of edges. But that's not really a proof, because perhaps when you get to 10 edges, 15 edges, 100 edges, vertices, perhaps there's something funky going on that you don't imagine could happen. So if you look at Prim's algorithm, because it does say here, justify your answer through a consideration of Prim's algorithm, you start with any vertex, and then you add 1 edge at a time until you have all the vertices. So how many edges are you going to have? Well, you're not going to have an edge for the first vertex, but you're going to have an edge for the second one. You're going to add 1 edge to get the third one. You're going to add 1 edge to get the next one. So via Prim, V vertices does imply V minus 1 edges. So our simple example there does lead to a consideration which makes sense, assuming Prim's algorithm is correct. Question 4. The following graph shows the offices of a finance company. So here's A, here's F, 9, here's E, this is 10, this is 6, this is D, which is 8, this is B, this is 11, A to B is 9, B to D is 10, B to C is 8, C to D is 7, and A to D is 12. You do have to be careful when you have edges crossing other edges to know, we're very careful about putting dots at vertices so that we see where those two things meet is not a vertex. You can always kind of redraw a graph all the way around, but there are actually situations where you can't avoid it and edges have to cross. So the following graph shows the offices of a finance company. The management wants to connect all the offices with extremely fast internet cables, but the costs of doing so in thousands of dollars are indicated on the graph below. So of course, what do we want to do? We want to connect them all at minimal cost. So A, use Kruskal's algorithm to find the minimum cost for connecting all the edges, all the offices, list the order in which the edges are connected. No problem. So we're going to start via Kruskal with the edge of least weight. I have a 6. So A to E is a 6. That takes care of that one. I also have a 7. So up here, C to D is a 7. I have a couple 8s. I have D to E is an 8, and I have BC is an 8. AB would be a cycle, so I'm not going to include that one. AD would be a cycle. I'm not going to include it. BE would be a cycle. I'm not going to include it. AF would not be a cycle, so I will include it, but FE will be a cycle, so I will not include it. I forgot to list the order. So it was first AE, CD, BC, and ED were both 8, and then AF is 9. What's the minimum cost? Well, we just add it together. 8 plus 8, 16, 16, 32, 38. So min cost is $38,000. Now, part B. It says, state how you would adapt the algorithm if it is essential for offices B and D to be connected. If it's essential that B and D are connected, I will start with a connection between B and D with their cost. If it's necessary, okay, put it in. And now do exactly the same thing. Start with the minimum weight of what's left that does not form any cycles. So what do we have? We have a 6, which is A to E. Okay, so those two are in. Next is 7, C to D. We have an 8, D to E. We also have an 8, BC, but that would form a cycle. B to E would form a cycle. A to B would form a cycle. We have A to F, which is 9, which would not form a cycle. And then F to E would form a cycle. And what is the minimum cost for this scenario? Well, 9 plus 6, 15, 25, 35. This would be $40,000. So it's good that the total cost is more than it was before, because if it was less, we'd really be worried that our minimal cost algorithm or minimal spanning tree wasn't actually the minimum. Okay, question number 5. Okay, question number 5. It says, use Prim's algorithm to find the minimum spanning tree for the following tables. Okay, so this is like the one we did earlier. We have 5 points, A, B, C, D, E, A, B, C, D, and E. We have 0, 40, 25, 15, 20, 40, 0, 25, 45, 30, 25, 25, 0, 15, 35, 15, 45, 15, 0, 20, and 20, 30, 35, 20, and 0. So go ahead, please, as usual, and pause and try to do this. So we're going to use Prim's algorithm, which means we pick any vertex. So I'm going to pick vertex A. So what do I do for vertex A? I cross out, first this is my first one. I remove everything in vertex in column A. Orange might not be the best color, so let's try something a little darker. So A is number 1, cross out everything in A, and then we pick D. So A connects to D with a weight of 15, and D is my second choice. Cross out everything in D, and now when I look at A and D, I see a 15, and that's D to C. So C is my third choice. Cross out everything left in C. And when I look at those 3 rows, I see a couple 20s. Either A to E or D to E, doesn't make a difference which one I use. So I'll use A to E. And that's 20. That's my fourth choice. Cross out everything else in that one. And now we look at the 4 numbers for B, and I see that one is number 5. So that's C to B, and that will be 25. Okay, so that is the minimum spanning tree for the first one. And then let's do part B. That's another 5 by 5. A, B, C, D, E, A, B, C, D, and E. I have 0, 4, 7, 9, 12, 4, 0, 8, not 6, 5, 3, 7, 8, 0, 10, 5, 9, 5, 10, 0, 6, and 12, 3, 5, 6, 0. So let's go ahead and use Prim's algorithm, starting with A, because why not? Cross out everything in A, and A connects to B. So 1 and B is number 2. So A connects to B, B is 4. Cross out everything in B, and the smallest number is B connects to E with 3. Cross out everything in E, and the smallest number left in those 3 rows, I got a couple of 5s. I'll do this one here. B to D, 5. D is 4th. Cross those out. And the smallest number left is 5 again. And that's E to C. And that is my minimal spanning tree for that one. Part C. Comments on why it will be more difficult to use Kruskal's algorithm than Prim's algorithm when the information is given in a table. For Prim's algorithm, you're taking a vertex, which you can pick from a table, A, B, C, D, or E, and then you pick the edge that connects to anything that you've already chosen of minimal weight. With Kruskal's, you're just picking any edge anywhere of minimal weights, which means you have to look at the entire table versus only a few or 1 or 2 and so on rows. The more vertices you have, the more rows you have to look at. But in the beginning, 1 row, oh, there it is. Or 2 rows, there it is. But if you look at the whole table, then you got to identify the smallest number in the table, make sure it's not part of a cycle, and that's just more work. It's not that you can't do it, it's just more work. So I'm just going to leave this blank, and you can just write down what I just said. Question 6. The following table shows the distances between homes needing to be connected to a mains water source at A. The distances between homes needing to be connected to a mains water source at A. Find the minimum length of pipe needed to connect all the houses and draw the corresponding spanning tree. All right, well, let's first make my table. This one has 7, A, B, C, D, E, F, and G. A, B, C, D, E, F. Think ahead. A, B, C, D, E, F, and G. 0, 20, 17, 23, 11, 10, 15, 20, 0, 9, 16, 21, 15, 10, 17, 9, 0, 22, 16, 10, 12, 23, 16, 22, 0, 19, 13, 18, 11, 21, 16, 19, 0, 16, 12, 10, 15, 10, 13, 16, 0, 25, and whoops, 15, 10, 12, 18, 12, 25, and 0. Okay, so again, the following table shows the distances between homes needing to be connected to a mains water source at A. I don't know what they mean by that. Does that mean that if they all have to be attached to A directly, then it's kind of obvious. So I don't know what they mean by needing to be attached to a mains water source at A. I really don't know what they want for this. But looking at the answer, I do see that it's just a standard question. So I think the way they phrase it is just weird. It says, find the minimum length of pipe needed to connect all the houses and draw the corresponding spanning tree. So we're going to use Prim's algorithm, starting with A. So I cross out everything in A, and I picked F, which is 10. So A was first. I get 10. And that's my second choice. I then cross out everything in F. And then in A and F, I see a 10 right there. That's F to C. So C is third choice. Cross out everything in C. And now look in those 3 rows, I see a 9. C connects to B with a 9. So B is fourth choice. Erase everything in that column. Next smallest number in those 4 rows, I see a 10. So B attaches to G with 10. So G is now number 5. Get rid of, get rid of, get rid of, get rid of, get rid of. So now I have those 5 rows. I see an 11, and that seems to be the smallest. So A goes to E, which is my 6th choice. Get rid of all those with 11. And then the smallest number left is 13. So F goes to D with 13. And when I add it up, 11 plus 10 plus 13 plus 10 plus 9 plus 10, I get that the minimum length is equal to 63 units, whatever it is. B. It is decided that A and B must be directly connected. Find the extra length of pipe that will be required. All right. Why do they do this to me? So first, let's. Okay. So it's decided that A and B must be connected. So here's A and here's B. And A and B are connected with 20. So that's a must. A and B must be connected. Which means if A is our first choice, B is our second choice, and we can connect A to B, which is 20, and then cross out everything in A, and then cross out everything in B. The next smallest number between those two rows is B to C. That's 9. That's my third choice. Cross out everything in C. First 3 rows, I see 3 different 10s. I'll just take the top one, which is A to F. That's a 10. And so F is my fourth choice. I still see some 10s. I'll take the next one, which is B to G. So G is my fifth choice. And I see an 11. So A to E. I cross out everything in E. And then what's left? I see a 13. F to D is 13. So notice that essentially all we did is we removed the FC connection, replaced it with a AB connection. So we removed a 10, we added 20. So now the extra length is 10 for a total of 73. And finally, question number 7. It says use Prim's algorithm to find the minimum spanning tree for the graph represented by the table shown. So this one, I gotta make a bigger one. A through H. A, B, C, D, E, F, G, and H. A, B, C, D, I. A, B, C, D, E, F, G, and H. But most are not connected. So oops, that's here. 7, 6, 3, 4, 6, and 4. And I'm just gonna put these in here. Oh, look at that. I completely missed it. It's a good thing I did this. I completely missed a column. 5, 6, 5, 3. So those. Okay. Okay. So this is part A. Part I, it says use Prim's algorithm to find the minimum spanning tree for the graph represented by the table shown. All right. Well, let's first start with A. A is my first choice. I'm going to remove everything in A, and I see that A connects to E with 9. So E is my second choice. Oops. And then when I look at the 2 rows for A and E, I see that E connects to F with 5. So, okay, get rid of that. And then when I look at those 3 rows, I have a 3. that wasn't there before. F to G with 3. G is now my 4th choice. I have 4. G goes to H. 4. That's my 5th choice. Let's see, I have a 6. Oh, I have, looks like 6 is the smallest. That's H to D. So D is my 6th choice. And now what's my smallest? I have a 7. I have a couple 7s. I'll just do the first one. Oh. Oh, no. That's it. I got a 5. That's D to B. That wasn't there before. Okay. So B is my 7th choice. Cross out B. And now the smallest number. Oh, wait, how come these weren't crossed out? These should have been crossed out. And then the smallest number now is 7 again. And that's A to C. 7. Let me just check it. I kind of feel that I missed a couple things. I want to make sure this is correct before going on. This is 7. A. Yeah. Well, theirs is different than mine. Let me just check whether my weight's the same as theirs. 7 plus 9 plus 5 plus 3 plus 4 plus 6 plus 5 gives me 7, 9, 5, 3, 4, 6, 5. I got 39. They have 38. So let's try this again and just be a little more careful. I'm going to use a different color. I realized halfway through that I was using the same color. So, okay, so we start with A. So A is my first. We remove everything in the column of A and we pick the smallest connection to A, which is to E. Oh, no wonder it's not E, it's C. 7. 7 is smaller than E. Oh yeah, so A, C, you make one stupid mistake like that. Okay, so C is my second choice. Cross out everything in C. 10, 12, 9, and 8. I have a C to B connection, which is 8. So B is third. Cross those out. Next, B to D is 5. Cross that out, that out, that out, and that out. Oh, in the first 4 rows, I have a 6. D to H. 6. H is out. That gives me a 4. H to G for 4. So G is 6. Now I have a 3. G to F for 3. And finally, the smallest number on the table is F to E, which is 5. 7, 8, 15, 20, 30, 38. Okay. I weight is equal to 38. Okay. And then finally, part B. It says a 9th vertex I is to be added to the tree. In the graph, I is connected to vertex A and to vertex B. So we have a new I, which let's put up here because it connects to A and it connects to B. By consideration of your tree from part A, find the weight of the new minimum spanning tree if I the weight of the edge to A is 9 and B is 10. So notice now I have a cycle. So I want to pick the smallest numbers I can that will not have the cycle. So I have to get rid of any one of those 4 will do it. Because if I get rid of the 8, I can go 10, 9, 7. If I get rid of the 7, I can go 8 and 10, 9. But if I get rid of the 10, we want the new minimum weights. We want to get rid of the most possible. So we want to get rid of the 10. If we get rid of this, so essentially all we'd be doing is be adding 9. In this case, the weight would be 47. If on the other hand, the weight of the edge connected to I is 5 and to B is 6, then in this case, I'd want to get rid of this one. And this one. So I'd be replacing a 7 and an 8 with a 5 and a 6, which means the weight would drop by 4. So the weight would equal 34. Now they say the weight should be 41. Oh, I need C still. So I have to keep the 7. So I have to keep the 7, and the answer therefore will be 41. Okay, fun stuff. And that takes us to the end of 15.3. So I'll see you next time in 15.4.